drawbacks or limitations of the first law of thermodynamics, and then only there was a need for the second law of thermodynamics. So let us first try to understand this. So today is the third day of myself transacting the lesson, that is chemical thermodynamics. It is a Monday and it is 15th of November 2021. Now, so I will first try to explain you one important application of the first law of thermodynamics. So one important application of the first law of thermodynamics, it is called Joule. It is called Joule Thomson. Joule Thomson effect. It is called Joule Thomson effect. Now, what is Joule Thomson effect? Let me explain you with the help of a diagram. Okay. Now, I will draw a simple diagram, a very simple diagram. Okay. Now, this part which you see over here, it is a plug, porous plug. It is a pipeline. It is a pipeline. It is a pipeline. This part is a pipeline. Okay. Now, this part, this left hand side, this left hand side, this is right hand side of this porous plug. This is a porous plug.
We haven't shared the screen.
Porous plug. Can you see the screen?
No, sir.
You cannot see the screen. Okay, let me share the screen. Wait. Okay. Can you see the screen now? Can you
Yes,
see the
sir.
screen now? Okay, good.
Yes,
Now,
sir.
on your screen, you can see one important application of the first law of thermodynamics. And that important application of the first law of thermodynamics, it is called Joule-Thomson effect. In this diagram, you can see there is a pipeline. There is a pipeline over here. There is a pipe, cylindrical hollow pipe. Okay, and it is divided by a porous plug through which there can be passage of gases. On the left hand side, there is a gas, compressed gas, compressed gas. Okay, and it is kept at pressure P1 and temperature T1. Okay, it is compressed at high pressure. Okay, now this gas is allowed to pass through the porous plug. So when it is allowed to pass through the porous plug, okay, then on the other hand side, the right hand side, the gas comes out and it is found that the gas is expanded gas. When it comes out this side, it gets more space, so the gas expanded gas at pressure P2 and temperature T2. So when this phenomena is done, when a compressed gas, highly compressed gas, when it is passed through a porous plug or a throttle, and this porous plug is made, it can be made of cotton, it can be made of silk. Okay, so when this highly compressed gas is passed through a porous plug from a region, say from a region of high pressure, there is high pressure over here, compressed high pressure, to a region of low pressure under adiabatic conditions. Under adiabatic condition means there is no what you call exchange of heat. There is no exchange of heat. That means dq is zero. So whenever there is no exchange of heat, when the gas, highly compressed gas, is passed from a region of high pressure to a region of low pressure, then there is causing expansion of the gas when there is a sudden change in temperature. Sudden change in temperature. That means the temperature can either be, what you call lowered, or it can be increased suddenly. So this change in temperature, it is called Joule-Thomson effect. So this is one important application of Joule-Thomson effect. So this is not there in the class 11 science syllabus, this application. But why I am doing it? Because it will help you for your competitive examination, the name itself and the meaning of Joule-Thomson effect. Okay, so that is clear, I think. Now, After this, we move further in this chapter. So I hope you got the idea what is Joule-Thomson effect. I repeat it once more. When a highly compressed gas at a pressure kept at a pressure P1 and at a temperature T1 is allowed to pass through a porous plug made of maybe silk or cotton, then the gas expands on the other hand side where there is change of temperature. There might be sudden change of temperature, and this sudden change of temperature, it is called Joule-Thomson effect. Now change this passing of the gas to the porous plug, it is happening under adiabatic conditions. It is happening under adiabatic conditions. Adiabatic condition means there is heat change. Heat change is zero. The amount of heat change is zero. So this is one thing you have to remember. Okay. Now only the meaning of Joule-Thomson effect. Nothing more than that. After that, let us try to understand some limitations of the first law of thermodynamics and why there was a need for us to study the second law of thermodynamics. So here I go proceed further. Limitations. Limitations of the first law. First law of thermodynamics. Limitations. So let us discuss them one by one. Now the first one says like this. The first law does not put any restriction. The first law does not put any restriction on the direction of flow of heat. That is an important point. The first law does not put any restriction on the direction of flow of heat. That means it does not define in which direction the heat is flowing. Okay. Now, for example, if we remember, it is not impossible to extract heat from ice. It is not impossible to extract heat from ice by cooling it to a low temperature and then use it for warming water. It is possible. It is not impossible. But according to our common experience, such a transfer of heat from a lower temperature to higher temperature is not possible without doing some external work. So it is not putting any restriction on the direction of flow of heat. That is the first law. That is a limitation. The first limitation. The second limitation is this first law. It is unable to explain. It is unable to explain why do the physical and chemical processes why do the physical and chemical processes occur in a natural direction. Okay, now this first law is not it has not been able to explain why the physical and chemical changes which are happening, processes which are happening, occur in a natural direction. It is not been able to explain. That is the second limitation. The third limitation is like this. This first law is unable to predict. It is not able. It is unable to predict. It is unable to predict the feasibility. It is unable to predict the feasibility of a process in a particular direction. In a particular direction. So it cannot predict. It is not able to predict the feasibility, whether the reaction will proceed in the forward direction or the backward direction. It is not able to predict. Okay. That is the third limitation. Then fourth limitation is this first law of thermodynamics. It is unable to explain. It is unable to explain why it is not possible. Why it is not possible to convert heat energy heat energy into an equivalent amount of work. It is not possible to explain this. Okay, so these are some important limitations of the first law of thermodynamics. I repeat them once more. The first limitation is the first law of thermodynamics does not put any restriction on the direction of flow of heat. Okay, from the example of extracting heat from ice, and uh, that heat is being used to do some work. It is possible only when we can use that heat extracted from ice to do some external work. The second limitation is the first law of thermodynamics is not able to explain why do the physical and chemical processes occur in a natural direction. If we pour water, the water will not go in the upper direction, it will go in the downward direction. So this has not been able to explain by this law. Then third one is the first law of thermodynamics. It is unable to predict the feasibility of a process in a particular direction. It cannot explain whether a direction will proceed in the forward direction or the backward direction. The fourth one, the first law of thermodynamics, it's unable to explain why it is not possible to convert heat energy completely into work, an equivalent amount of work. So, because of these limitations, there was a necessity for us to understand and come to the next law, which is called second law of thermodynamics. Now, this law, the second law of thermodynamics, it was able to predict the direction in which energy can be transformed, and the direction in which a spontaneous change can take place. So, because of the limitations of the first law of thermodynamics, we have after that the next law, which is called second law of thermodynamics. The second law of thermodynamics. Now, let us proceed further. Before going to the second law of thermodynamics, I feel it is necessary for all of us to understand some important terms which will be required again and again in this chapter. So I'll just refer to your textbooks after the limitations. So if you have a look at your textbooks on page number around 372, my textbook, it is coming to 372, article 6.4. Article 6.4. If you have your textbooks, you can turn it. If you don't have, then you can follow the screen. Article 6.4, there is written over there heat capacity, specific heat capacity, and molar heat capacity. These are terms which are not new to you. I can understand. Heat capacity you have learned in class 10 in physics chapter, even specific heat capacity and molar heat capacity. Now, let us deal this according to this chapter, chemical thermodynamics, and understand these terms first, and then only we will deal with the second law of thermodynamics. First one is heat capacity. The definition: the quantity of heat required to raise the temperature of the system by 1 degree Celsius. Okay, so if there is a system or a substance, so amount of heat which you provide to that substance to raise its temperature by 1 degree Celsius, it is called heat capacity of the system. It's 1 degree Celsius either or Kelvin. Now, here in this chapter, the heat capacity is represented by capital C. Capital C. Now, if you consider small q as the amount of heat required to raise the temperature of a system from a temperature of T1 degree Celsius to T2 degree Celsius, then you can make a formula. Heat capacity is equal to Q, that is the quantity of heat required to raise the temperature of a substance from T1 to T2. So, C is equal to Q by T2 minus T1, or you can write equation 6.24, heat capacity is equal to Q by delta T. Heat capacity is equal to Q by delta T. So this formula you remember. Heat capacity, that is C is equal to Q by, you can write delta T. Now how do we get delta T? We get delta T by subtracting T2 minus T1, because it is the amount of heat required to raise the temperature, which means T2 is greater than that. final temperature is greater than the initial temperature. This has to be kept in mind. Okay, so on this basis, we can derive, we can get a differential equation for heat capacity where C is equal to Q by dt. This is a this is a differential equation. This is a differential equation for heat capacity. And I have told you already, definition of heat capacity is the quantity of heat required to raise the temperature of 1 gram of a substance or a system uh, by 1 degree Celsius. That is called heat capacity. That is not 1 gram. Raise the temperature of a system by 1 degree Celsius. Now, the other word over here, that is specific heat capacity, small c. Specific heat capacity is represented in this chapter as small c. Now here, the specific capacity of substance is the amount of heat required to raise the temperature of unit mass. So whenever the mass comes into play over here, then we have what? We have specific heat capacity. A unit mass of a substance, maybe 1 gram or 1 kilogram or 1 quintal, whatever, by 1 degree Celsius or 1 Kelvin, then it is called specific heat capacity. So when mass is included, the heat capacity becomes specific heat capacity. So the formula is C is equal to Q, small q, divided by mass m into T2 minus T1, or Q is equal to m delta T. This is also one formula which you have learned in class 10. Q is equal to mc theta, no? Q is equal to mc theta. You have learned in class 10. Q is equal to mc small c, and you have learned theta in class 10. Or we can write m small c and delta T. So that is the you can say a formula relating the quantity of heat, okay, mass, specific capacity, and the rise in temperature. Okay, so here we have the specific capacity from this chapter. Moving further, the second column over here. Now, since the heat capacity, remember, it is a function of temperature, so it would be more appropriate to express the above equation in this form. It is a function of temperature. That's because temperature is changing. Remember that. Temperature is changing over here. In this case, the temperature is changing. So remember, C is equal to, small c is equal to Q by mass into dt, because it is a function of temperature. Where, what does Q mean? Q means an infinitesimally small amount of heat absorbed by m mass of the substance to raise its temperature by a temperature dt. After that, coming to molar heat capacity, number of moles, Cm. The molar heat capacity of a system is defined as the amount of heat required to raise the temperature of 1 mole. Not unit mass, now it is 1 mole. Now when mole enters, then we have the heat capacity being called as molar heat capacity to raise the temperature of 1 mole of a substance by 1 Kelvin. So again, this Cm, the same formula from above, takes another form. Cm is equal to Q by T2 minus T1, Q by delta T. Now this value of m, number of moles, is 1 mole. Okay, so since the heat capacity varies with temperature, it would be appropriate to define molar heat capacity in the form of this differential equation. Cm is equal to Q by dt. Whenever you use d, it is a differential equation which you are looking at. And again, similarly here also, this Q is what? It is an infinitesimally small amount of heat being absorbed by the system to raise the temperature by Kelvin by dt. Okay, now looking at the CGS system, the units, normally the molar heat capacity is expressed in the units of calories per Kelvin per mole. Please try to remember this. Units is calories per Kelvin per mole. Calories per Kelvin per mole. That is important for you to remember. However, its SI unit, it is joules per Kelvin per mole. The SI unit is joules per Kelvin per mole. Okay, that is more important. Okay, try to remember that. Okay, that is joules per Kelvin per mole. Now, for a system, particularly for a gaseous system, whenever there is a system involving gases, the heat capacity measured at constant volume is quite different from that measured at constant pressure. Hence, there are two types of molar heat capacity. The two types of molar heat capacity are this one. Molar heat capacity at constant volume, that is CV. At constant volume, the molar heat capacity is written as CV. and at constant pressure, the molar heat capacity is written as Cp. So, if I ask you the question, what are the two types of molar heat capacities? Your answer should be the heat capacity, the amount of heat required to raise the temperature of 1 mole of substance by 1 Kelvin at constant volume. That is molar heat capacity at constant volume. Whereas, if it is happening at constant pressure, if the amount of heat required to raise the temperature of 1 mole of a substance by 1 Kelvin at constant pressure, it is called molar heat capacity at constant pressure. So, make this definition very clear in your mind. Cm for 1 mole, it is Q by delta T. Remember this, learn this formula. 6.28 equation, okay, a differential equation. Then this derivation part is there. A relation between Cp and Cv is required. It's very, very important in class 11. So we'll discuss this briefly. So number one, molar heat capacity at constant volume. It is given by this formula. We know 6.229, and also we know QV is infinitesimally small amount. Why CV? Why QV? Because this is the heat exchanged at constant volume. That's why we're writing, instead of Q only, we're writing QV over here. Now, where QV is an infinitesimally small amount of heat. Infinitesimally means very, very small, minute amounts, which is absorbed by the system at constant volume to raise its temperature by Dt. So you can write QV, since QV is equal to change in internal energy, whereas delta U is an infinitesimally small increase in the internal energy of the system. Hence, equation 6.29 can be written in another form. CV is equal to, substituting the value of QV, we can write delta U by dt at constant volume, or CV is del U by del T within brackets. The volume is written in capital, that is constant volume. So this is one formula which will help us to work out the relationship between Cp and Cv, molar heat capacity at constant pressure and molar heat capacity at constant volume. Thus, my dear students, the heat capacity at constant volume may be defined as the rate of change of internal energy with temperature at constant volume. So this is one important definition for us to remember. This one, this definition. This is one important definition. Please better learn it. Heat capacity at constant volume may be defined as the rate of change of internal energy. Internal energy is changing with respect to what? Temperature. Okay, and it is happening at constant volume. Okay, that was molar heat capacity at constant volume. Now coming down to the second one, brief discussion only. If you look at the molar heat capacity at constant pressure, Cp, sorry. So the heat capacity at constant pressure, we know from above, Cp is Qp by dt, where Qp is again infinitesimally small amount of heat being absorbed by the system at constant pressure to raise its temperature by dt. So again, this equation takes the form Cp is equal to Qp is at constant pressure, so we can write delta H. Delta H means what? Enthalpy of the system. Change in enthalpy. So change in enthalpy enters over here whenever the pressure is constant, at constant pressure, or you can write Cp is equal to del H by del T at constant pressure. Therefore, this relationship takes the form heat capacity at constant pressure may be defined as the rate of change of enthalpy with temperature at constant pressure. So this formula, this definition also you must remember. Now, by having a knowledge of equation 6.30 and 6.32, it is possible to work out a relationship between Cp and Cv, because we know Cp stands for molar heat capacity at constant pressure and Cv stands for molar heat capacity at constant volume. Okay, boys, can you hear me? There was a disruption in the internet connection. Can you hear me, boys? Can you hear me, boys?
Yes,
Okay, there was a internet connectivity problem on my side. Can you hear me now? Okay,
yes, sir.
okay, good. Now let us continue. Today there is a lot of disturbance in the internet connectivity and the power as well. No problem. Anyway, we shall proceed further. So I was talking about this heat capacity at constant pressure. Equation 6.32. It is the rate of change of enthalpy with temperature at constant pressure, and this CV, the molar heat capacity at constant volume, it is the rate of change of internal energy with respect to temperature at constant volume. So using equation 6.30 and equation 6.32, it is possible to work out a relationship between CP and CV. So I request you all to thoroughly pay attention to this. Remember, CP is greater than CV. So a relationship between CP and CV can be obtained as given below. We know from the previous chapter, that is study of gases, an ideal gas for 1 mole PV is equal to RT. The change in enthalpy at constant pressure, that is delta H, is given by the formula. Delta H is delta U plus P delta V. Now here what we have to do is, for 1 mole of a gas, PV1 is equal to RT1 and PV2 is equal to RT2 at constant pressure. Pressure is constant. So P V2 minus V1 is R T2 minus T1. So we can write P delta V is equal to R delta T. Now we know delta H is equal to delta U plus R delta T. Instead of P delta V, we have put what? R delta T, and worked out a relationship over here. Delta H by delta T is equal to delta U by delta T plus R. Now we know delta H and delta U are infinitesimally small. We have this, instead of delta H by delta T, we are putting Cp. This is Cp. This is Cp, and this one is Cv. So Cp is equal to Cv plus R, or we can say Cp minus Cv is equal to R. It is a constant. So this equation 6, this derivation will be required. So how to start the derivation? If the gas is assumed to be ideal, then for 1 mole of a gas, we can write PV is equal to RT for 1 mole of a gas. Okay. Now, after that, the change in enthalpy at constant pressure, we know the formula from the first law, delta H is equal to delta U plus P delta V. Okay. That is from the first law of thermodynamics. And for 1 mole of an ideal gas, we can write, put V1 and V2 in this equation. So PV1 is equal to RT1 and PV2 is equal to RT2. And make over here P delta V is equal to R delta T. And instead of P delta V, we are putting R delta T and then dividing delta S by delta U, delta T over here on the both sides. Okay. And then we get this form over here. So, but we know delta H by delta T is at constant pressure and delta U by delta T is at constant volume. So this is Cp and this one is Cv. So Cp minus Cv becomes R. So this equation 6.33, it represents a relation between Cp and Cv. From this equation, you can clearly say that the difference between the molar heat capacity at constant pressure and at constant volume is equal to a constant, and that constant is what? It is called a gas constant, 8.314 joules per Kelvin per mole. Okay. So based on this derivation, there's a numerical. There's a numerical which you can see on the screen. Example 6.9. Example 6.9. It's given 10 moles of a gas. Number of moles is given at constant volume from, it is heated at constant volume from 20 to 30, that is 10 degrees Celsius, right, rise in temperature. Calculate the change in the internal energy of the system. That means you find delta U. The molar heat capacity of the gas is given, Cp is given, and value of R is given. And since we know Cp minus Cv is R, so Cv can be found out easily because Cp is given. So, and R value we take, it is in what you call calories. So we'll use R to value 1.987. So put the value directly over here and get the value of Cv. Okay, Cv is got 4.83. Now apply this formula, Cv is equal to Qv by delta T. Qv, the heat absorbed by 10 moles of the gas from 20 to 30. So that will be Qv is equal to 10 into Cv into delta T. So 10 into Cv we have got 4.83 into delta T is 10 degrees Celsius. So it's coming 483 calories. Now since heating is carried out constant volume, so delta V is 0. The work done is also 0. So according to the law of thermodynamics, we know This is the equation which I've learned from the first law of thermodynamics in the previous classes. So delta U is equal to Q plus W, and we know over here W work done is 0. So put the value of work done 0. So delta U internal energy becomes change in internal becomes 483 calories. Okay, so this is a direct problem based on the relationship between Cp and Cv. By using the Cp and Cv values, we are calculating the internal energy change. Similarly, equation 6 point, example 6.10 also. Another question. There's a gas expanding from 3 decimeter cube to 5 decimeter cube against a constant pressure of 3 atmosphere. Pressure is constant. Okay. The work done during expansion is used to heat 10 moles of water at temperature 290 Kelvin. So they are telling us what will be the final temperature. Calculate the final temperature of water after it is being heated. Okay, so there is expansion. The gas is expanding. The gas is doing work. It is expanding from 3 to 5 decimeter cube. So work done for it is an irreversible expansion. It is expanding irreversibly at constant pressure. The pressure is constant. How much? 3.0 atmospheric pressure. So based on this concept, work done is minus P, V2 minus V1. So getting the value of work done. Okay, minus 3 into 5 minus 3 is 2. It's coming to minus 6.0 liter atmosphere. That is 6.0 liter atmosphere. Okay, and then over here they are multiplying it to the gas constant and getting converting this into, this is how to convert liter atmosphere into joules. Liter atmosphere into, because 8.314 divided by 0.0821, it is the factor to convert liters atmosphere into joules. Okay, this you must remember. Then we get the work done is minus 607.6. So here this work it is used to heat water. So let the delta T be the temperature, change in temperature. So Cp at constant pressure, Qp by m delta T. Okay, then Qp becomes equal to minus W. That is, this Qp is equal to minus W. So it is 607.6. So delta T is Qp by m Cp. So put the values over here. Mass of water we can obtain 10 into 18. Okay, number of moles into 80. So Cp is given 4.14 joules per Kelvin per mole for water. This is coming 0.807 Kelvin. So we have to add 290 plus 0.807 Kelvin. It is come to 90.807 Kelvin. Okay. So these are the two problems you should practice. You should practice for using the relationship between Cp minus Cv is equal to R. Okay. So now the main concepts over here, molar capacity, specific capacity, and the heat capacity is clear, and the relationship between Cp and Cv is also clear to all of us. But make sure you revise this. It is very very important. These two sums over here, example 6.9 and example 6.10, very very important examples. And then only after that, in the next class, I'll be starting with the second law of thermodynamics. The second law of thermodynamics I'll do in the next class. So today I would like to stop my class here only. But before that, please hang on over there, because I need to, what do you call, record your attendance. Okay. Okay, your attendance is downloaded. Okay, it is downloaded. You can leave the class and join the next class. Thank you so much. Have a nice day.
Thank you, sir.